In this video, I'll talk through what the motivation is behind studying the subject of fluid mechanics. The applications are tremendous, so I'll only restrict my attention to just a few comments I wish to make and also try to tie it with some of my own personal research, which involves combustion and fluid mechanics. So the applications of fluid mechanics is quite broad. It spans many time and length scales. As an example, if you're looking at drug delivery or blood flow, it involves a fluid, and it involves a fluid pushing a drug into a human being, for example. If you're looking at flight, whether it's birds or airplanes, you involve fluid mechanics in one fashion or the other. Likewise, for any energy generating devices such as wind turbines or for power generation purposes, if you're looking at cooling water circulation for a power plant or combustion engines like your automobile, these are examples in which fluid mechanics does play a role. Likewise, when you're talking about local weather or even global circulation models, where fluid mechanics plays a role at very large scales. And we'll watch a quick short video. My goal is not to watch the entire video in this course, but just to give you a sense.
The first step to explain how global circulation patterns affect weather and climate is to understand how temperature varies across the globe. Global circulation is caused by different parts of the world heating up differently. In this first video, we will look at what causes this differential heating. The sun is our main source of heat. This heat travels to us through space in the form of radiation. This radiation is absorbed by clouds, atmospheric gases, and by the Earth's surface. Some parts of the Earth receive more of this radiation than others. The main reason for this is the curvature of the Earth. This curvature means that at higher latitudes, the radiation from the sun is spread over a much larger surface area, while the same amount of energy is much more concentrated near the equator. The radiation also travels through a greater depth of atmosphere nearer the poles in comparison to the equator, so more radiation is lost to scattering and absorption by gases and particles in the atmosphere. The tilt of the Earth also means that polar regions do not see daylight during the winter. Here the Earth is continuously sending out heat to space, without any compensating incoming heat from the sun. These cold polar regions are where we see lots of snow and ice. Snow and ice, and also thick cloud, reflect a lot of the sun's radiation back into space. The reflectivity, or albedo, of the underlying surface is an important factor in determining how much of the sun's radiation is used for heating the Earth. The combined effect of all of these processes sets up a thermal gradient between the equator and the poles. In fact, the global radiation balance is such that poleward to 40 degrees latitude, the outgoing heat radiation from the Earth exceeds the incoming heat radiation from the sun. Global circulation acts as a clever air conditioning system, redistributing the heat.
So that's the main idea, that the global circulation systems acts as a mechanism of redistributing heat in the atmosphere at global scales. Here are some other examples of fluid mechanics. This first picture is actually taken from the book, and it looks at the flow stream going around a cylinder. So here, right here is a cylinder, and the flow is rendered, visualization of the flow is rendered by putting some kind of a dye in the flow stream, and what you can begin to see is what the streamlines might look like. So this looks like very nice, what is called laminar flow. If you look at the picture at the bottom, these are actually results of computations that a former graduate student of mine performed. So what we have here is we have a high-speed fluid coming up on top, and we got a low-speed fluid at the bottom, and these two are meeting and mixing at the edge of this splitter plate. And so what is formed are these vertical structures that get formed, and these vertical structures represent transition from laminar flow essentially to sort of the beginning of transitional flows. And what you can begin to see is this is a mechanism by which you're able to mix fluid. So what's colored over here may be a dye that I'm trying to mix between the high-speed fluid and the low-speed fluid, and this might play a role, for instance, in a fuel injection system, where the goal might be to mix the fuel and the oxidizer effectively. The picture again on the top over here is from the textbook, and shown here is sort of the streamline pattern, if you will. But you can see that the streamline pattern kind of breaks down on the backside of this airfoil element, which is situated over here. And the flow actually separates from the upper tip of the airfoil, and the flow becomes turbulent fairly quickly in this region, right? But away from this region, the flow still appears to be quite laminar. So the nature of the flow that is set up over here explains what might be the drag that this object might experience, or what might be the lift force that this object might experience, and that's obviously of relevance for flying purposes. These two pictures at the bottom are taken from that I took from experiments that we performed in 2008 in Portugal. So this is an experimental facility where we have a fire that's being burnt on a surface, and what we're looking at is a fire front, and then the goal is to try and understand what are the attributes that determine the rate at which this fire might spread. And this includes sort of the fluid mechanics in the region right around the fire. The picture on the right is from a prescribed burn in the outdoor field. And what's dramatic about this picture is you see a fire going up a slope actually, and you see the shrub that is burning, and a part of the shrub is burning below, but part of the shrub is not burning at all. And this is very characteristic of what happens in a forest when you have fire go through a forest, right? And so we're trying to understand sort of the fluid dynamics behind processes like such. This is an example of an experimental facility that was done about 8 or 10 years back. And what you're seeing is here's a fire front that you can begin to see. It's actually proceeding in the direction along the flow direction, if you will. And then what we're doing is we are cutting this by a laser sheet, and the laser sheet is used to reflect particles that in the fire. And looking at the movement of these particles, we are able to discern what the vertical velocity components are in this plane of the visualization. And so here, for example, is a rendering of the actual velocity vectors that you see. And so you can see a large velocity here, and this starts propagating to the right as the fire goes from left to right in this picture. So this is from a camera view that's taken looking from the edge, from the side on the previous diagram. So these are examples in which fluid mechanics plays a role, and hopefully you get a sense of why we might study a subject such as fluid mechanics.